This video goes over Chapter 18 homework, problems 8, 12, and 15. I used the template as much as I could. So for problem 8, they want you to draw the project. So I like to always have a start and a finish node. And then this is the precedent relationships that they're given. This is in this one they didn't give you any probabilistic times, so all they did was just give us activity times. So how I made the template do that is I reproduced these numbers over in the optimistic, most likely, and pessimistic, but if you noticed, I just made them the same numbers. So when you take the average of the same thing, you get that number. That maybe was overkill, but that's how I did that. There's no variance because they're constants. They're constants. But once you calculate that, the model will automatically put a yes. I went ahead and added some conditional formatting, but the template will give you if it's on the critical path. So the critical path goes through A, B, E, H, and I. So A, B, E, H, I is the critical path, which is the longest path. And since there's no variance, the project completion time is 31 weeks. So problem 12 asks you to shorten it by 3. And you could formulate this as an optimization model and use solver and let solver determine exactly which activities to crash. Other than that, it gets kind of difficult. So there's an algorithm that you can follow, and what you need to do is focus on the cheapest cost, the cheapest crashing cost per time, and it has to be on the critical path. So for the very first one, your choices are activity A, activity B, activity E, H, and I. Those are on the critical path right now, and the cheapest is either this one or this one. It needs to be the cheapest, and it needs to be on the critical path. So you're either going to crash activity B or activity H. The issue is that you want to crash one time period at a time, because when you crash and you shorten a project, a path, it may no longer be on the critical path. So I think I'm going to choose H. I don't know if you have to, but I'm going to use H. So I'm going to go back over here, and you can notice that I can only crash it by 1 week. So I'm going to go over, and I'm going to take activity H, and I'm going to make this now 3. And you can see it reduced my average expected project length from 31 to 30. And I can't crash it anymore. And these costs per time should be, let me make those constants. Okay, I'm going to take these and turn them into constants, because that's what they are. But I am going to crash this one, the cheapest one, 3. All right. I look over here at the critical path, and it still runs through A, B, E, H, or I. So it's the same ones, except I can't crash activity H anymore because it's as short as it can be. So I now have to crash activity B. And activity B, I can shorten it up to 2 time periods. I'm just going to shorten it 1. Again, and if you have to do it 1 at a time, because if it jumps off the critical path, there's no reason to keep doing it. So I'm going to cut this down by 1 time period. And you can see I reduced it by this. Now my critical path runs A, B, C. So actually I have 2 longest paths now. I got one that runs through A, B, E, H, I, A, B, E, H, I, the original one, and now one that runs through A, C, E, H, I. So I could go to B again and maybe crash it, but look what happens. If you crash B, you're probably not going to get a bang for your buck. And look what I'm going to, if I do that, because as soon as you do this, the critical path jumps to activity C. So if I drop this one down to 6, it didn't help me at all because the critical path jumps through activity C. So that's not a good one, and I probably shouldn't crash activity C just because it's expensive. So I'm going to go to the next one, which is activity E, and I'm going to crash it for my third one. So I'm going to put this back to what it was. And I've crashed activity H and activity B both by 1 week, and the last one now I'm going to crash is activity E, and I'm going to crash it by 1 week. And there I got to this, and that cost me $250. So it cost me $200 plus $200 plus $250 for a total of $650 of crashing cost in it to shorten the activity from 31 to 28. The last one is just getting the probability of meeting a due date of 27. We're given probabilistic times because we have different optimistic and pessimistic times, so we now can calculate an average and a variance. So once you type these in for activities A through G and then put in the precedent relationships, when you draw the network, you can see that both F and G need to be attached to the finish node. The other way to know that is that in the book you can see that activities F and G are not listed as immediate predecessors, so they have to be linked to the finish node, both of them. And once you calculate it, put those in, the expected, the average, not the exact, but the average finish time is 21 weeks, but we do have variability, so we have a standard deviation over a project of 2 weeks. So the likelihood of meeting a due date at 27, you can look at it as a normal distribution problem. What's the area to the left of 27 on a normal distribution centered at 21 with the standard deviation of 2? The probability, I can use the norm dist function, and it comes up to be really high. So quoting a due date of 27 is probably a good idea. If you would just quote this 21, if you would just quote that, well, you would get 50%. So you don't want to quote the average when we have variability in our project activity or activity times. Thanks.